want to just to change just a little bit. All right. So yeah, this is a course on lead groups. We did our best to find at least 4 or 5 applications to quantum info subjects. But for the first couple of weeks, we're just going to have to survey a bunch of stuff in lead groups. There's not that much. It's actually easy to survey everything there is to know from a superficial level. So hopefully we can do that in the first 3 lectures. Yeah, so if we can go to syllabus. Yeah, here we go. So today we're going to be going over, well, what is a group, and going over the 2 canonical families of examples, finite groups and matrix groups. And I'm even going to explain to you guys a little bit about their classification theorems. And then next time we're going to go into matrix groups from the perspective that they're continuous, and therefore have a local structure, and therefore talk about Lie algebras. Okay. And then in session 3, we're going to go back into the classification of Lie groups and do the real deal. Okay. So the 2 buzzwords are universal cover and accidental isomorphism. Yeah. Don't worry, they're very easy to comprehend things once you know what they are. Yeah, so I guess we need to coordinate who is going to give which lecture. I've already seen session 3, someone has yet to volunteer for, but I think session 4, Austin was excited to do. Anupam wants to do session 5. Session 6, I don't think we've found someone yet, maybe Gopi. And I know Raph liked the idea of doing session 7. So the last 2 sessions, 8 and 9, I don't think are necessarily classes that have to be there. We can go into representation theory. Or we've got 5 other topics that came up, so there's yet another list of things you might be interested in. So it all depends on interest again. So topic A is about, well, how do you actually calculate R measures, let alone using their fancy properties to do orthogonality relations. Sometimes you really need to know its measurements. So if you're interested in that, maybe we should do one of those instead. Invariant theory is always wonderful. Speckens likes to call these generalized conserved quantities because they're not always bilinear in the wave function expectation values of an observer. Yeah, SPTOs is something I know some of us are interested in. So if you wanted to talk about group cohomology, that could be a class. If you wanted to talk about wavelet theory or the normalization group, that can be a class. And if you want to think about the Weil-Heisenberg group as an analytic signaling person, to think of it, that could be a class. So yeah. Is there anything else?
Just a few comments. So we'll talk in the following days and weeks about who gets each session. We have a website that you can access from the physics departmental website. Should be the last homepage.
Yeah, classes at the top there.
Yeah, and also
Yeah.
here and over here. On this website, you can find the updated syllabus, which is not updated now because Chris changed it half an hour ago. And there will be, well, we have lecture notes from today, thanks to Chris, that are already uploaded. And then for the idea for session 1 and 2 at least is to have a set of exercises which are easy to do, and I think they're a good practice to kind of use the things that we'll see kind of abstractly perhaps in some of the lectures and in just using them to work out problems. And so we already have the problems for session 1, which are here. That's 4 problems, and you can also find the solutions.
Oh, already, since we already, but that's, wait till next week.
And so the same.
Or never.
We'll go for session 2, and just to comment, after session 2 we'll have a 1-week break because both of us will be out of town. So we'll have more problems for you guys to do so that you don't get bored. And that's it.
So I guess we do need to figure out when to do the makeup, because third week we will not have class.
Right?
All right, are there any questions?
Remember a test?
I
We
don't
haven't
think
decided
so.
yet.
Okay.
An oral quiz, yes.
Final project.
All right. Well, if there aren't any questions, I guess we should get started. Is this a poll? Alright, so I guess the best place to get started is simply to ask the question, well, what is a group? So I'll give you the dry definition first, and then maybe spend 5 minutes just talking about what its bits
Hey,
actually
Chris.
mean.
Can you speak up a little?
Yes, of course.
Thank you.
And could you keep me loud? I might dim down every 10 minutes or so. Who knows? Okay, so formally, a group is a set. Okay, with a multiplication. And this is an interesting and kind of deep concept, multiplication rule. Okay, and what counts as a multiplication rule is an operation that has the following 3 properties. That, first of all, there exists an element in the group that acts in a way that basically it doesn't act. Right? This is a thing we call an identity. But it also has inverses. There's a cute little sort of thing you can do in your mind about this exchange of existing universal. But finally, the multiplication is, if you're a mathematician or an algebraist, you'd say associative. If you're a physicist, you probably want to call this property Markovian. Okay, so associativity / Markovianity. Okay, so, loosely, well, rigorously, Markovianity, because the actual value of this iteration of multiplications only depends on what's going on at the junction of the 2 elements, right? You're not using a different multiplication rule depending on the entire string that you have, right? But you can also think of these as maps and time going in one direction, in which case this might feel a little more Markovian. All right, so just to be a little clever, notice that all I did is say that there exist left identities and inverses. In fact, you can prove that this implies there exists a right inverse in identity, and they are equal to the left inverses in identities. And that can have a nice spiritual connotation to it if you tell a story about what multiplication orders mean. Okay? Are there any questions on the definition?
Typically, I've seen closure included as a part of the definition.
Oh,
Are you,
sure.
Are you
Yeah.
implying that?
That's a good point. So let's comment a little bit on what it means to define a set. Yeah, so I guess I'm already implying closure, right? So when I think of a set, I think of what I call an imagined property, right? How do you define a set? Usually say a set is the set of all things with this property. And indeed, it is assumed that this multiplication rule continues to preserve that property. Okay? And indeed, this is related to Noether's famous theorem that anytime you have the notion of a conserved property or quantity, right, there is a group that articulates this fact. Did that answer your question?
Yeah, thanks.
Great. So, yes, there is closure. And almost by definition, right? Because if you imagine a property and you suddenly realize you can do something that introduces a new property, well, then you extend your notion of property.
So in this case, you're defining the set by the properties of its elements rather than enumerating the elements themselves?
Yeah, I don't know how to enumerate something without listing a set of properties. You'll see that all of these groups we're going to define, they sort of require, we're assuming the existence of some property, right? The set of maps that do this, the set of matrices that have that property. Did that answer your question?
Yeah, I guess we're assuming it that, okay. I mean, yes, it did, thank you.
Oh. Let's not get too spiritual. I don't remember what I was going to bring to you. Okay. So the first group to always think about is the symmetric group. So it's important that this abstract multiplication we've defined can always be thought of in terms of compositions of maps. Okay. So if you need something that's a little more concrete, you should think of it as just composition of maps. Which brings the canonical example of the symmetric group. So it's always given the name Sn, and it's just the set of invertible maps among n elements. Okay. So to be more specific, let's do the quick example of permutations among 3 elements. Oh, by the way, these are also called permutations, right? Okay, so let's call the 3 elements 0, 1, and 2. Well, there's 6 operations I can do that are distinct and invertible. So let me try to arrange the list of, move this over. Okay. So there's, of course, the identity operation. Take everybody to themselves. And then there's this guy, which has 2 as a fixed point, and this guy, which has 1 as a fixed point. This guy, there is a fixed point, and then you've got these guys. Okay. So of course, if we want to talk about the permutation of many elements, it's going to get quite cumbersome drawing dots and arrows between them. So there's what's called Cayley's cyclic notation. Okay, so what you notice, right, is every permutation can be described as a set of cycles. Right? In this case, we've got just single element cycles. In this case, we have a 2-element cycle and a 1-element cycle. Same with these two. But then these two have 3-element cycles in them.
Chris, can I just ask, just to be clear, the
Yes, of
arrows
course.
themselves are the elements of the group?
Are the maps, yeah, so I could
The
also.
map is the element of the group.
uh,
So when you say
The map
group-
is the element
Right.
of the group,
Each
yes.
group, right, so each arrow is a particular element of group, and that,
So,
Each set
yeah,
of
this is the map, pi of 0 is 0,
yep,
pi of 1 is 1, pi of 2 is 2, and I would say pi is an element of S3.
mhm.
Right. All right, are there any other questions? All right. So in Cayley cyclic notation, we don't bother describing the fixed points. So if every point is a fixed point, we just call it the identity. So in this case, we get a cycle of 2 elements between 0 and 1. This guy, we get a cycle of elements between 0 and 2, 1 and 2, 0 going to 1, going to 2, and 0 going to 2, going to 1. Okay? And because we understand that these lists in parentheses represent cycles, it doesn't matter the order we write them. So this is the same as 2, 0. And this is the same thing as 2, 1, 0.
The order matters, but it's up to,
The order matters, but the cycle doesn't
Yes.
matter. Did I say, oh,
he
thank
says
you.
the order doesn't matter.
Whoopsie. All right. Okay. So, if you ask me, what makes groups the most interesting is the fact that they can be non-abelian. And we already encounter non-abelianity in this example. Actually, but before, oh no, yeah, this is great. So a group is abelian and this term is so second nature to me, but it just means non-commutative. It means commutative. Okay. So if, right, for every 2 elements in the group, order doesn't matter. Okay, so now, real quick, another very important group to give a name is the cyclic group. So the cyclic group is defined as basically a list, so it's called Zn. Certainly you see Z2s and Z2 cross Z2s and stuff everywhere. Zn is defined as a list of elements, n elements, call them A squared, A cubed, such that the lowest power of A, that is the identity, is n. Okay, so I've introduced power notation, I guess. So A to the P is just A times itself, P times. Okay. And as you can see, hopefully, this is an abelian group, right? It's basically the only abelian group there is. Yeah. Are there any questions?
Is there something in the notation we say group G is abelian if for all G and H in G, is that equal?
For all G and H, oopsie. That just doesn't make any sense. Uh-huh. Great. Are there any other questions?
Did you say this is the only deal you move to finite number, does it matter?
For finite.
Yeah.
Yeah.
I mean, if I have infinite continuous groups, there must be more.
It's not much fancier than
Yes,
this.
but it's
Yeah.
something a little bit different.
Yes, exactly. All right, so the reason this is called cyclic, right, is because you can imagine these are sort of chained in a circle, right? And you've got some original element, and you've got a notion of hop, right? And you come back to where you came from after you've hopped n times. And as Ivan is already alluding to, well, if you have a continuous group, you can certainly have differential hops. But it turns out that's basically it. Yeah. Are there other questions? Yes.
So what is A then? Because when I see this,
Yeah.
math BBC way of.
Okay.
ridiculous, right?
Sure, so a representation of this, if this makes you feel better, is I can take A is an nth root of unity in the complex numbers. Okay. This is a representation of this type. Okay. Sort of being agnostic to the fact that I technically know how to do much more with these than just multiply. Right? But we're trying to distill the spirit of composition. Did that answer your question?
But doesn't it also come from like addition of integers mod n or something?
Which is exactly the same
Right.
thing, yes, indeed.
Just a different
That's
way of
what's so
saying it.
great about the exponential map, is it mods itself, yes.
So that perhaps is truer to the Zn notation.
Oh, okay.
Zn is Z modulo nz.
Okay. Yeah, yeah. If you want to do the mod by hand, if you want to let a function do it for you, great. Are there other questions? Okay. So on to the classification theorem. So we're not going to talk much about what a simple group is until section 4. But I think for now it suffices to say that there is a notion of a basic building block. Okay? So, roughly speaking, there are only 4 basic types of finite groups. Now, don't let the simplicity of this theorem trick you into thinking there isn't a lot here. Okay. So 1, there's cyclic groups. And to really understand what this means is really to understand number theory. Okay, what are primes, etc. Then there's what I'm just going to call permutation groups. To really understand this family is to understand the nature of algebraic solutions to equations. And then things get really diverse. There are groups of Lie type. Which, in spite of, remember we're talking about finite groups, in spite of the name of this course, I don't think we're going to get to discuss at all algebraic groups of Lie type. But maybe a little bit. Their names are inspired by many structures that you see in continuous Lie group theory. And finally, there are the 27 sporadic groups. There's a little bit of controversy in the community about whether the 27s should be here or here, and the special name is called the TITS group. All right, are there any questions? Again, this is rough, so you need to clean up. Okay. Like for here, it turns out you need to think about permutations of 5 elements before you start getting new stuff that you wouldn't have gotten in here. And this is related to the non-existence of a quintic formula, which is cool.
This,
Yeah.
what do you mean when you say basic types?
Yeah, I said, what I mean is simple groups, and I won't be able to define what a simple group is until section 4. Is that, because
Yeah.
simple means there exist no normal subgroups, but why do we care about normal subgroups? Because they allow us to build. And this notion of building is very different from a cross product. It's called a semi-direct product.
But so
We'll have a whole class on that.
any finite group can be made somehow using pieces of these.
Yes.
That's
But the actual details of construction are still an open problem, actually. Yeah. But you know that such decompositions exist. Are there other questions?
So, you know, where do these like braid groups lie in this?
Yeah, so you can write a braid group as hella semi-direct products. I haven't really spent a lot of time with braid groups, but maybe we can figure out what the semi-direct decomposition of the braid group is. Yeah, that's the best answer I can give you. But I don't know the braid groups personally. Other questions?
Great.
Hmm.
So by
well,
finite group, are we, should I understand a group with a finite number of elements or a finite number of generators?
A finite number of elements.
Okay.
There's no such notion as a generator yet.
Well, so
Well,
sometimes
he brought it there in
people
the
call this
cyclic group,
A,
yes.
the
Yeah.
generator of the group. Yeah. In fact, we might as well introduce that notation now. Okay. So angle bracket means everything you can make out of group multiplication. And indeed, it's important that we're restricting ourselves to a finite number of elements. Yes. Otherwise, the story changes again. Yep. Other questions? All right. Of course, the star of the show is not finite groups. Of course, finite groups are always going to emerge, which is why we discussed them. But the stars of the show are matrix groups. So, or really Lie groups. So again, roughly speaking, all finite dimensional matrix Lie groups. So a Lie group, and we'll discuss more of these subtleties next week, is a continuous group, roughly speaking. I don't know why I had to capitalize this one. So the notion of a continuous group can get really deep. Okay, and there are even, for example, we're going to talk about Hilbert's fifth problem, which is a question about, really, are Lie groups just continuous groups? Yeah, there's a bunch of controversy about the answer to that question. Okay, so every finite dimensional, so hopefully we can all just rely on the intuition that once you have continuity for whatever topologies we're going to use, you have a notion of dimension. And then I can say that every finite dimensional Lie group is equivalent to a matrix group. And hence, we're just going to talk about a bunch of matrix groups today, and then we'll end with another classification theorem. All right. Are there any questions? This is what I believe is called Ato's theorem. In case that's useful.
Whenever you say finite dimensional Lie group,
Mm-hmm.
do you mean like it has some finite dimensional representation? Some finite
No, yeah. You can think of it as it can be embedded in R.
It's a dimension of the manifold,
Yes.
ultimately.
Yes.
So that's the space is continuous space, it's a surface, and it's got some.
Yeah, so if you don't want mathematicians to argue with you, oopsie, You can just put smooth here, and then there's no debate. This is the right definition of a Lie group. Okay. In which case you have a notion of taking derivatives, sort of put together a bunch of tangent spaces. Think about how that lives in an ambient space. Right? And once you know what the dimension of a tangent space is, that is the dimension of the group. Assuming it doesn't have the ability to proliferate dimensions. Did that answer your question?
Yeah.
Okay. Are there other questions? How am I on volume?
You're good.
What's a matrix group?
Yes, all right. And that's the perfect question. That is the question to ask. So these two lines, I guess, were just to justify why the hell are we talking about matrix groups. So what is a matrix group? Okay. A matrix group is a subgroup of the general linear group. So I'm going to write this as like 2 sentences. Topic, the general linear group. Okay, this is given a name. GL of NC. It's important that we're going to be starting with complex entries for our matrices, and hopefully why we're doing this is going to become clear as we go through and start knocking out all the matrix groups there are. But maybe some of you are aware that complex numbers are algebraically closed, which means you cannot devise a solve for x polynomial problem that would somehow make a new number. And that's related. Okay, but this is the set of n by n matrices with entries in C. Of course, I need to say there exist inverses, so put an invertible here. And of course, the multiplication I'm going to equip this set with is matrix multiplication. Did I answer your question? Are there any other questions? Okay. So before we proceed to describing more groups, actually no, we should just describe one particular group. Thinking about these guys, so really, this looks like a boring example, but it turns out to have many secrets in it. So GL1C, what is that? Right. You think about it. Okay, so the only element of the complex numbers we definitely don't want to include is the 0 element. Okay, so I'm going to denote that by complex numbers take out 0. Okay. And maybe I'll give this guy another name. We'll call it C0. Some people like to call this C cross. Okay. So this guy has two real forms. So you can think of it as a two-dimensional group, right? It's got a real and imaginary direction. And it has what are called real forms. So one of them is the abelian group that I think Ivan was alluding to. It's called the circle, more commonly known in physics as U1. Okay. And I'm going to write it in a funny way. I'm going to write it, it's the set of Z in C naught such that Z minus star is Z. Okay, so minus star is just take inverse, then conjugate in whatever order you want. Does everybody feel like this is equivalent to their usual definition of U1? Perhaps you're more likely to say something like this. All right, but it's got another real form, which I'm going to call e to the r, which by the notation is going to be the set of elements that are the exponential of a real number. All right.
Should
Hmm?
there not be an I or something?
Hmm? No.
E to
No, not at all. Yeah, so let's draw this out. So there are two real forms of C0. One of them is the circle, but then the other one is the ray. Okay. Sometimes this is called the line. Mathematicians like to be a little pure. And I can multiply real numbers, positive real numbers, and they stay on that line. So they're closed under that property. Which then, does that answer your question? So if I don't include an I here, I'm not talking about this space. So I guess I could describe this as the set of Z and C naught, such that there is an X or a phi in R, such that Z is a phase. That's another way to define the U1, in which case I should include an I.
Is that C is equal to e to the x?
Z is equal to, oh jeez. Yeah, I'm just speaking nonsense. Yes. Thank you.
Could you just define a couple of things that you mentioned?
Please.
Subgroup and real form?
All right. So I guess I'm about to define real form. I just wanted to give you two notions of subgroup that have half the dimension of this complex group. Okay. So, so then the definition, I guess, should be a subgroup is a subset that is closed under multiplication. You can think of it as a subclass, a subproperty. And then a real form.
But, sorry, and so does that imply that the identity
That
that
they
you
have
have
the same identity. Indeed.
are unified?
That's great, yeah, so this guy has one in it, these are wonderful points, and this guy also has a one in it.
But I mean the general definition of subgroup.
Yes, you can prove that such subgroups have to have the same identity as the M.
Okay.
You have another question I didn't answer, a real form. I think we'll define here as is a subgroup of, thank you for this question, by the way, it's exactly the question you have, of half the dimension. With half the dimension with let's say defined by a conjugation. conjugation is defined as something that when you do it twice, you get nothing, and it's going to respect the group. So hopefully these are good examples. This guy I can define instead as the set of Z and C naught. So this one's a little awkward because I have to cut it, so let's define the easier one, which is R naught, which is the set of real numbers modulo 0. And the thing to notice about this one is it's not connected like the circle is, right? Because when you took out 0, you cut the real one in 2 pieces. But this one is easier to define in terms of a conjugation, right? Okay. Are there any other questions?
So things like transpose and dagger would count as conjugations. Right?
Almost, yes. We will be going through all of those soon. Yeah. Great. Okay, so now before we move on to other matrix groups, there's a special map we need to introduce, which I'm sure many of you know well, called the determinant. And I'm going to say it in kind of a fancy way. So the determinant, right, is a map. I think the most straightforward way to define it is to say it's a map from GLNC to C0. This double arrow just means it's on 2. And we're going to define the map as, this is a det DET. Det M is, I think, the most useful way to write it is in terms of this anti-symmetric symbol. So it's a polynomial, an nth order polynomial in the matrix elements of M. So often you might see this formula as fixing J1 through Jn, but I found that it's much more useful to use this formula. So this term, every term that appears here, appears n factorial times, which is what this division is for. Okay, but this is in fact the same as so what is epsilon? Epsilon is the permutation symbol. So if I define pi of k as equal to I sub k, then I might as well just write this as epsilon sub pi. And then that's what's called the sign of the permutation. So another way of saying this is just, so epsilon, no, we have to say this first, I'm sorry. So epsilon 1, 2 up to n is by definition 1. And then depending on how many paired permutations I have to do, the sign flips. All right, so this is a very important map, and it has the property that it is what's called a group homomorphism, which means that the determinant of the multiples of two things is just the multiples of the determinants. All right. Which brings us to the special linear group.
For a second, what was pi of k? Was pi of k?
Yeah, so this I'm thinking of as a permutation of the numbers 1 through n.
Okay.
So I'm saying I sub k is the first entry, is where pi takes 1. So, got it, is that, okay. So this is not 1, 2, 3 to n. It's some permutation of 1, 2 to the n. So that's what that means. And then Anika.
Is there a relationship between this epsilon, the value that the epsilon symbol takes with, to the permutation group that you talked about earlier?
Yes. How do I answer that further without starting a new discussion? Yeah, I don't think I
I
can.
think you answered it.
Yes, okay, so of course it's permutations, right? It can't be very far from the permutation group. Indeed. Are there other questions?
Is pi a number or an operator?
Pi is an operation. Yeah, uh-oh, right. It's a, so I defined, so when I look at this, I see a string of numbers. And I'm saying, I'm considering a string of numbers such that the kth entry is just the image of what a permutation would have mapped the number k. So don't think about it too hard, because this is in a sense redundant. It's just two ways of saying the same thing. Right? This is just a number, a line of distinct numbers, which are a permutation of the numbers 1 through n. Did that answer your question?
So how does -1 for pi? That I don't understand.
Oh, okay, so I guess you can say this is -1 to the number, okay, that's okay. -1 to the number of nearest neighbor permutations. How's that? I think that's the, yeah. Does that answer your question?
Yeah.
Just feel like you could calculate the sign in a sense.
There's common fact or common that indeed any, maybe it's true, but any permutation element can be made from just flipping two things. And so you just count whether
Yes.
the number of to get from that string to whatever string you want to do, you just count how many of those you need to the unique number. And if
Yes.
it's even or odd, you put a -1. Which Chris already said. I'm just,
Did I? Okay.
but it's
Thank you. Thank you.
redundancy is good.
Yeah, as you guys can tell, I'm not much of an algorithmic thinker, so I'm sorry if I define something in a way that doesn't tell you how to calculate. Because these things are not hard to calculate, so make sure to ask me those questions. Are there any other questions?
One request, can you write a little bigger?
Write a little bigger?
Yes.
Yeah. Would you like me to rewrite number and permutation?
No, I think it's fine.
Okay. So SLNC is simply the set of matrices in GLNC with unit determinant. So other fancy ways to define this are, you think of det as a map, then it has an inverse image. So this is the set of all things that evaluate under the determinant of 1. And the inverse image of the identity of a group has a special name. It's called the kernel. So it's also Ker det. Oh, doing great on time.
The kernel normally the thing that maps to 0.
Under vector space
Yeah,
homomorphism.
sorry.
Yeah, exactly.
So the group kernel is the thing that get mapped to the identity.
It just it respects multiplication. It doesn't respect any notion of addition like that. Did I spell determinant correctly?
Yes.
Okay, so the special linear group turns out to be one of the basic building blocks, but it has 4 of these so-called real forms. Okay. Actually, it has more than 4, but you sort of stick a bunch of them into one family, as you'll see. Okay, so the real forms of SLNC are, well, perhaps you can guess one of them, SLNR. And the conjugation is, well, entry-wise complex conjugation. Another real form. You know, did you guys think this was curious? I remember when I was first doing quantum. SUN has half the number of real dimensions as SLNC. That's
I've never
fun.
noticed.
I thought that was funny. But indeed, this is a profound fact. Okay. Oh, Jesus. Okay, and in this case, the conjugation is inverse dagger. It's probably a funny way to think about unitarity, but certainly equivalent to what you would call unitary.
So how do I see that SUN has half the number of elements as SLNC?
Yeah, so to actually count the dimensions is only easy to do locally. So we'll do all of our dimension counting next week. Yeah, so right now, I guess I'm asking you to believe me that they do have half the dimension, but I will tell you how to calculate their dimension next week. I'm sorry, that's the best answer I can give you.
Yeah, I guess I also was, going back, I guess I didn't really absorb the meaning of real form.
Okay.
So real form was defined as a subgroup of the general linear group that is of half dimension defined by conjugation.
Yes.
So once you define a conjugation, that someone constrains things to be, what does it mean to say defined by a conjugation?
Right, so here, the conjugation is, so M chi is M inverse dagger.
Okay.
And I guess we need to show it's a conjugation. So sure enough, Mn inverse dagger, what is that? If I do it twice. And you see, that's just going to give me Mn. I guess I didn't need to put two group elements in there, but I do.
Okay.
And then also, it has the homomorphism property. So let's do them one by one. So inverses have this rule,
Sure.
and dagger is going to flip yet again. And hence we have something we can call a conjugation. Conjugate is a product of its conjugate. And the same is true for entry-wise multiplication. So all of these are defined by this conjugation.
But defined by conjugation means that once you define a conjugation, then the elements are set by their constraint that M conjugate equals M.
So when you say defined by a conjugation,
Yeah.
you mean given a
Defined
constraint
as
of a
invariant
conjugation,
under a
that's a, yeah,
conjugation.
that is invariant in
Yes.
a conjugation, then that constrains it in such a way, then that's called a real form.
Yes, that's
Okay.
exactly right.
Okay.
Thank you.
Just like the reals are the things that are conjugates of themselves.
Exactly.
And that's a real form.
Got it.
Cool. Did everybody get that? Would you like me to write it down?
Be useful to write it down.
Okay, so let's try again with this definition. A group is a real form a matrix group is a real form if it is invariant under it is invariant under a conjugation. A matrix group is a real form if it is invariant, if
If its elements are invariant under a conjugation.
elements are.
So the business about half the dimension is follows from this, or is it a part of the definition? I guess that's what was confusing me.
Yeah, this halving property is going to become very clear when we do the local
It follows from this, but the definition is just about the invariance.
Matrix group is a real form if its elements are invariant under the conjugation, and it is a subgroup of a complex group. Okay. So there's only going to be 3 examples of complex matrix groups. One of them being SLNC. Okay. Are there any other questions?
So if I understand it right, SLNR is a real form of SLNC,
Yes.
and SUN is a real form of SLNC.
SLNC. Yes. Yes. Great. And there are 2 more. All right. Well, there's a few more. So there's SU R comma S, where R plus S is N. So I'm going to need to define something called GRS, which is just going to be the diagonal matrix of R by R minus S by S identities. So SU R comma S is, again, it's a real form, so it's a subgroup of SL and C. And the conjugation is GRS inverse M inverse dagger GRS equals S. So let's prove real quick this is a conjugation. So Mn, call this thing chi. Well, Mn chi is just, well, I can stick in GRS's wherever I want. So we already showed that inverse dagger is a conjugation. Right, and what's great about conjugation by matrices, it's unfortunate that has exactly the same name. Conjugation by matrices, I can just stick in a GRS inverse. Okay. All right. So if you look carefully, you see that, well, SU n comma 0 was already defined, right? But we're never going to write SU n comma 0. All right, and then there's one more. And this one's a little odd. So it requires me defining this matrix omega, which I'm going to define as 0, 1, minus 1, 0, tensor an n by n identity, or k by k identity. And which is the same as in case this makes your brain hurt. It's just a bunch of diagonal these guys. Yeah, so SU 2k star.
Is that the convention?
Yeah.
You don't want to make them zero, a large zeros by 0 block. A large.
Choose it however you want. But I want these blocks to be kind of broken up because, yeah, it turns out that you can think of every 2 by 2 block as a quaternion. So it's really nice to, that's how I imagine it, is these 2 by 2 blocks are sort of new kinds of entries. But I promised myself I wasn't going to say the word quaternion.
shouldn't the tensor product be the other way around? One tensor product, then.
Have I been thinking about it backwards this whole time? This is how I do it.
Oh.
Yeah, and I've done it like this for, I think this is how most algebraists do
I
it.
read you put the one tensor, the other thing.
Well, so I
That's the way
think,
we typically do it.
yeah, okay, interesting, because I think of this thing on the left as a coefficient. And so I think of this as a k by k matrix with entries, right? And so this looks just like what you would call something like C times psi, for example.
But that's,
It's
not the-
arbitrary.
It's not the standard order that we use in physics.
That's very, I'm sorry. Well, you can choose your favorite definition of tensor product, you still get the same group. Cool. And this definition will be, it's the set, again, it's a real form of SLNC, defined by the conjugation M inverse dagger omega omega inverse.
A naive question. Do you require that 2k equals n?
Right, yes. For n equals 2k. Exactly. Yeah, great. Fantastic. So indeed, not every n has this real form, only the even ones do. Great.
Why the star?
Because this is not the same thing as SUN.
Could be prime, it could be tilde,
Uh,
it is called it.
Why star? Because maybe because it's a real form, so like conjugation, it's its own thing defined by a star. So this is also isomorphic to, I'm going to say this and just know it as a fact. It's isomorphic to k by k matrices with quaternion matrix. Often. Yeah. Well, so if you look at a list of this classification I'm about to share with you, you might not see SU2K star. You might see this one instead. Don't panic, right? It's the same thing. Did I address, you made a comment, I remember.
No, it's just teasing you. She
Okay.
said you wouldn't use the word fraternity, but
I
you
see
did.
Can you finish writing n equals k over 2 for our viewers?
Oh, Jesus. Cool. All right, wow, that makes 15. So I think I'll go for another 15 minutes. Okay. That's definitely enough time. All right, because the rest of them are just speedy. And in fact, I think I can say them more quickly. So I've just introduced to you guys perhaps 3 new kinds of conjugation you've never thought about before, or maybe not realized you thought about. And indeed, those are it. I'm not going to give you a bigger zoo of conjugations. Okay, so now we want to define 2 more complex Lie groups, complex matrix groups. One of them is called SO2, SONC. Okay, so this guy is going to be, it's not a real form of SLNC, but it is still a subgroup of SLNC. Defined by property that it leaves the identity matrix under this operation invariant. So the reason I put that identity in the middle is I want to emphasize the fact that there's an entire geometric thing behind the identity matrix. So I'll give it a name, but we can discuss this outside of class. So the identity is actually a metric. What I mean by a metric is a positive definite symmetric form. So For example, it could have emerged out of the covariance matrix of some fluctuating order parameter that had a Gaussian distribution. And you then chose a basis, given the existence of that metric, such that you normalize the metric. Right, so it looks pretty trivial. It's not a diagonal matrix, it's just a bunch of ones. It's actually a very deep thing. So much has been cleaned up by the time you say, I have an identity matrix. Okay. That's just a little fact. And then one more. So we've got SP2NC. And that's the set of matrices in SL. Oh, so it's actually important. I have to take away the S. GL, 2NC. That's going to instead leave this omega invariant. Okay. And this omega has a similar story. Okay, so omega is a symplectic. Anti-symmetric, non-degenerate, anti-symmetric, for some reason the language deviates, so you never say a metric form, you just say a metric. But then you never say a symplectic, you always say a symplectic form. So this form sort of escapes the parentheses. Normalized. Okay, so these problems come from doing, variation, arriving at Hamiltonian mechanics, defining your conjugate pairs, and then you're done. Right? Then you have a normalized omega that you take for granted. A canonical omega, if you will. Are there any questions?
So this is not the same omega as what you wrote down on the left, right? It's something
It's
similar
supposed
to
be
that.
the same omega. Yeah.
But that
It's
is
the
two.
same.
That is 2 by 2, right?
What is the?
So the omega over there is a 2 by 2 matrix.
No, it's a 2K by 2K matrix. It's a tensor of a 2
Oh,
by 2.
omega is the whole thing.
Omega is this whole thing.
Okay. Sorry, I misunderstood.
No, no problem. Are there other questions?
Yeah, I was just gonna check. Generally, whenever I think, most people think of SON, we think of real value matrices. I guess this automatically implies that it's real value, though, right? You just kind of kept the C over there.
Perhaps could use that.
No, actually, this is a complex group. So, yes, this is not yet what you would call
SON.
SONR.
Oh.
Yes. So, in fact, what you would call rotations are what I would call a real form of this group.
Okay.
Yes, so I've yet to give you a condition. This isn't yet the rotation group.
Okay.
Okay, does that answer your question? All right. And then I think I'll just okay, we've got time. So I'm going to be a little briefer with my notation. I'm going to zoom in on these guys, and when I define sets, I'm not going to keep saying M in whatever. Okay, this squiggle bracket means in that group. Okay. So up here, we've got yes, of course, SONR, right, which is of course defined by M star equals M. I can also expand on this. So, yeah, this one's tricky. Okay, so then there's SO R comma S. So by the way, for many reasons, this thing is never called directly SONR. It's just called SON. Which will become clear at some point. It's the maximal compact groups being everything. This is the maximal compact group of SONC. Okay, so R comma S is defined by the same conjugation we had before for SL and C. Okay. If you think about this, this looks nothing like the definition of what you might call SO3, 1, for example. But they are isomorphic. So you would probably define this group as a set of M in SL and R, right, such that they have this property. And the isomorphism is take M and multiply it on the left and right by the square root of this guy. Pick your favorite square root. Convince yourself that that's indeed. Okay. Oh, there's another one. SO2K star. And it's defined exactly how we define the other guy. This is the conjugation. I'm going to move this isomorphism over so I have space. Okay, so those are all of the real forms of SONC. And then, for the symplectic group, Graph's favorite. And then there's SP2R, 2S, okay, which is going to be fixed under sort of a similar multiplication, right? Or a similar conjugation. You just have to double everything, right? So this G is just sort of append a couple of 2x2 blocks to this little g. So this is just a 2x2 identity. And then finally, we have, that's it. But one of them has a special name, SP2N. So be wary, there is not a consensus among communities on what to name these groups. So alternative names, I have like a red pen one. Alternative names for this guy is just to call it SP2N, or even just to call it SPN, 2. And also this guy has names, these guys have names. Sometimes they're just called SPR, S. And sometimes they're also called, and I don't like this, but it is a thing, it is a property of our world, that some people like to call these unitary symplectic groups. You put a big fat U in front of the SP. Okay. And maybe some people also call this USP2R, 2S. I haven't paid close enough attention.
But just the way you've written it, that, like, the symplectic and the orthogonal are related to
Right.
the,
So
which is, instead of transpose, you put a dagger, but it seems like you've
Exactly.
chosen.
exactly. I wanted to use a universal conjugation. So I think what Raph is pointing out is here, for example, I didn't have to write M inverse transpose. I could have just written M star, because by definition of the group, I have that property, right? So I'm purposefully not thinking of transpose as a conjugation. And you can apply, that's the problem, right? These matrix operations you can apply, but I would suggest that you maybe want to suspend transpose as representing something else than a conjugation.
I guess I was also saying that, like, over there, omega is playing a certain role, and you could write G of RS, sort of, in a similar way, instead of putting M by itself on the side,
Right. Are you,
which is the same.
are you saying I could just as well have written this? Yes.
Right.
And as, wait a second. I could just as well have written this as omega inverse M inverse transpose omega equals M.
Yeah.
Which would suggest that you should think about it as a conjugation. And yes, my comment was, I'm suggesting you do not think about this operation as a conjugation. You can for now if you want to, just keep in mind as you go on in your life, maybe transpose is something else. Did I answer your question?
Yeah.
All right. Having said all of that, we can finally arrive at the classification of simple Lie groups. Basically, that's it. But these things have funny names because of history. And these funny names you see in the literature, especially in random matrix theory and some crazy things Kataev likes to write. Wonderful, crazy thing. When I say crazy, it's always a compliment. Okay. Okay, so classification of simple. Again, I haven't defined what simple means, but for now, just think of it as a basic building block. So basically, there's only 5 families. Okay, so the first one is called AN. And this includes SLN+1C. And its real forms. Something about this is a little rough, but we'll clean it up in the 3rd class. And there's BN, which is SO2N plus, so odd SONs, and their real forms. CN, which is SP and C, and its real forms. DN, which is the even SO2Ns and their real forms. And just like in the finite group example, there are first, second, third, fourth, and then 5th. There are 5 exceptions. Only 5, not 5 infinite families. 5 exceptions. Which we'll call, well, they are called E6, C, and its real forms. E7C, E8C, F4, and G2. And I might as well tell you how many real forms they have. This guy has 4, 3, 2, 2, and 1. You never know when these facts come in handy. And that's it. Are there any questions?
How do real forms work for these odd dimensional cell?
So you just take exactly the same definitions we use for S. It's just we call the odd ones in these B, and we call the even ones D.
Okay.
Yeah. So these are exactly, these two are completely described here, right? Just sort of mixed together. Does that answer your question?
Yes.
Yeah, I don't know, that kind of brings up something for me, like, you said that the real form should have half the dimension.
Yes.
So what about these odd cases?
They all have half the dimension.
The real forms have.
All of these are even dimensional. Yeah.
And this one?
Right,
two
so
and
SO2 n plus 1,
Yeah.
half of that.
So 2n plus 1 is the dimension of the vector space being acted on.
Okay.
But there are 2
Oh, it's half the
plus
dimension of
1,
the.
choose 2
Okay.
dimensions in SO2n, because these are like rotations. So you pick a pair of vectors, and that defines a plane in which a rotation occurs. And then this is the number of independent planes,
Okay.
which is an even number.
Okay.
Great. Other questions? All right.
Can you repeat that? Can you repeat that?
Okay, what is this number? The claim is it's even. So what is that? That's 2n plus 1 time. Oh.
I mean, I see that it's
Well, first of all, right, so this is the number of complex dimensions. So the number of real dimensions is yet another factor of 2, right? Okay. Sorry. Okay. And then SO2nr, or SO2n plus 1r, has half those dimensions. Does that make sense?
no. I don't understand how you got that number itself. The 2n plus 1 factor.
Right,
Is it-
so
is it-
we won't count dimensions until we actually do the local forms of these groups.
Can I just comment? Is it clear that one thing is, these are matrices, right? One thing is the dimension of the matrix, and the other thing is the dimension of the
Group.
right?
Yeah.
Like in SU2. So counting that, as Chris says, right, counting the dimensions of the group will be easier to do by counting the generators, as in SU2, right? So the dimension of SU2 is 3, although the matrix is itself like 2. And that's the difference.
Okay.
That's the only comment. I mean, in terms of this, that's particularly for SO2n plus 1c, right?
Yeah, so I guess I was asking you to trust me, that is the
So, yeah.
dimension of SO2n plus 1c. Yes.
Yeah, but you were describing the way you can sort of see that intuitively, is that it's just rotations, and I want to do a rotation in a plane. So it's a question of how many planes I can put in a 2n plus 1 dimensional space.
Yeah.
So I just choose, I have 2n plus 1 dimensions, and I just choose 2 of them to be the plane that I rotated.
Okay.
Right, so
Yeah, that is
same thing
just
in
the
like 3
number.
dimensions, right? It's like
Oh,
3
okay,
choose
okay,
2,
yeah,
right?
yeah.
Yeah, because I choose, how many planes can I put?
Okay.
Yeah.
Now
Fantastic. Other questions?
So what exactly are these 6 and 7
Oh, gosh,
Exactly.
I don't know them personally. I've never had to interact with them.
They're just subgroups of it.
But they're matrices. They have matrix representation. They are the most elegantly defined in terms of how they respect tensor products of octonions with other division algebras. And otherwise, yeah, so so remember, I was suggesting that you think of transpose as not associated with the conjugation. And so we were defining these groups in terms of a bilinear. Yeah, so those come from octonion bilinears. I think that's the best answer I don't know more.
Sure.
Are there others like E5? It just happens to be.
Oh, yeah, so there is a method to the dimension. So it turns out that these groups are always associated with generalized eigenvalue problems. And that number in the denominator describes how many different eigenvalues a general element of the group can have. That being said, historically, these were constructed, E1, E2, they're all defined, but they're isomorphic to the other things we've already defined. Other questions?
So you have an omega defined when you find the for all these SL and SL, right? So this omega should also be odd dimension, right?
It should be even. I hopefully never used an omega for a non-dimensional case,
Yes,
did I?
but these methods are odd, right? This 2n plus 1, SO 2n plus 1 are
Oh,
odd.
right, but, so the omega conjugations could have only happened when you had an even.
Okay, for this Bn there is no real form
Yeah,
for
so
that
there
form.
is no real, yeah, so this real form doesn't exist in Bn. Okay, yeah, good.
So the number of real forms are less for An and Bn basically.
I wouldn't say that. There are, An has every real form under the sun, but sometimes N is odd, sometimes it's even. So there's this one funny guy who.
But there's an n plus 1 there, right? SL of n plus 1?
Yes. Right, and so when n plus 1 is even, there exists a real form, SU 2k star. And when n plus 1 is not even, it does not have the real form, SU 2k star. Yes. Good. Great question. Yes, I'm being very loose with those things. Takes a little just familiarity. Yeah, when it doesn't exist, it doesn't exist. Or when it's not defined, it doesn't exist. Is that a good answer? Okay. Yeah, so all the omegas are 2k by 2k. Yes. Great. Other questions? Well, thank you so much.